Okay, hey, welcome back, class. So we've been working through visualizing chemical bonds in 2 dimensions. Although your Lewis dot structures gives us a good idea how elements are going to bond together, it doesn't tell us how they're going to orient themselves in a 3-dimensional world. This is where molecular geometry comes in, and the VSEPR theory can aid in our understanding of how atoms bond to each other in the world around us. Our objective for today is to classify the molecular geometry of molecules using VSEPR theory. In saying that, let's dive into this. Since the lecture is going to be centered around VSEPR theory, we might as well know what does VSEPR stand for. VSEPR stands for valence shell electron pair repulsion. This theory is centered around the concept that like charges repel one another. Since valence electrons are negatively charged, the valence electrons of one atom will repel the valence electrons of another atom because both of them have a certain amount of free negative charges. This repulsion causes atoms to arrange themselves in very specific ways in order to reduce the amount of repulsive forces within the molecule. Remember, molecules want to be as stable as possible, so it's going to want to minimize this repulsive force. In other words, it's going to try to optimize the distance those electrons can be from each other. So let's look at a compound of ammonia, also known as nitrogen trihydride. Its chemical formula is NH3. If we look at the Lewis dot structure for ammonia, it would look something like this. We would have our nitrogen as our central atom, and it would be surrounded by 3 hydrogen atoms and have one lone electron pair. This lone electron pair is going to act upon other atoms within the molecule and repulse them, causing them to rearrange themselves more like this. If hypothetically we remove those lone pairs of electrons, the molecule will arrange itself so that the hydrogens are as far apart as possible. This shows us that the amount of lone pairs within the central atom affects the molecular geometry or how molecules orient themselves. In VSEPR, we represent atoms and electrons using the following. The central atom we are going to represent with the letter A. The atoms that are bound to the central atom are represented by the letter B, and any subscript after that letter is going to tell you how many of those atoms there are. And finally, the letter E represents unshared electron pairs. Any subscript after this is going to tell us how many of those pairs there are. If we go back to ammonia from earlier, we could use the template AB3E to represent it. Nitrogen be our central atom, A. The 3 hydrogens are bound to the central atom, so that would be B and our subscript 3. And then we would have one lone pair of electrons, our E. So, why is this important? Well, with VSEPR theory, you can use these templates to determine the molecular geometry. Let me walk you through all the templates for molecular geometry. First is going to be AB2, and it has a linear geometry. There is no lone pairs of electrons, so the atoms are going to be as far apart from each other as possible. An example of this would be carbon dioxide. Your oxygen will create a double bond with the central carbon and form what looks like a straight line. AB3 is a trigonal planar geometry. We have 3 atoms attached to a central molecule with no lone pairs. These atoms are going to orient themselves as far apart from each other as they can, creating a molecule that kind of looks like a Y. An example would be BF3, or boron trifluoride. Our next one is AB2E. So this is where we get our lone pair of electrons in. AB2E is a bent molecular geometry. And we finally get to bring in lone electron pairs into this. The lone electron pairs will push the other bonds from a straight line down to more of a bent structure. So an example of this would be ONF. Our next one is AB4, which is tetrahedral. It can be represented by methane. Then we go AB3E, which is trigonal pyramidal. A lone pair of electrons would push all the other atoms down into a triangle pattern. An example of this would be our ammonia atom. Then we'd have AB2E2. This is going to be treated like a bent molecular geometry. You have 2 sets of paired electrons that push down on the bonds farther than them apart, so they cannot form the linear format. An example of this would be water, H2O. Our next one is AB5, and AB5 is trigonal bipyramidal. in its molecular geometry. Think of an old school diamond shape. An example of this would be PCl5. Our final molecular geometry is AB6, and this is known as an octahedral. SF6 would be your example of this. Okay, now you know the basics of molecular geometry and what the templates look like, so you can start looking at chemical formulas and being like, hey, this one has this central atom and this one has so many other atoms bound around it. I know it's AB something. You can do your Lewis dot structure to figure out how many lone electrons it may or may not have, and then from there you'll be able to figure out its molecular geometry. So I hope this helped you out, and keep up the good work in class, and see you next time.